Welcome to the chapter on coils and inductance. In this chapter, we will explore the fundamental concepts of coils and inductance, which are essential components in electrical engineering. In this chapter, we will cover the coil, magnetic coupling, the switch-on process of a coil, switching off a coil, how much energy a coil can store, and a comparison between capacitors and coils. A coil, also known as an inductor, is a passive electrical component that stores energy in a magnetic field when electric current flows through it. The inductance of a coil, denoted as L, is a measure of its ability to store energy in the magnetic field and is measured in henries, abbreviated as H. The inductance of a coil is given by the formula L equals N squared times mu times A divided by L, where N is the number of turns in the coil, mu is the permeability of the core material, A is the cross-sectional area of the coil, and L is the length of the coil. Consider a coil with 100 turns. A core permeability of 4 pi times 10 to the power of -7 henries per meter, a cross-sectional area of 1 times 10 to the power of -4 square meters, and a length of 0.1 meters. The inductance of this coil can be calculated as L equals 100 squared times 4 pi times 10 to the power of -7 times 1 times 10 to the power of -4 divided by 0.1, which equals 1.26 times 10 to the power of -4 henries, or 126 microhenries. When two coils are placed close to each other, the magnetic field generated by the current in one coil can induce a voltage in the other coil. This phenomenon is known as magnetic coupling and is the principle behind transformers. The mutual inductance between two coils is denoted as M. The mutual inductance between two coils is given by the formula M equals K times the square root of L1 times L2, where K is the coupling coefficient, which ranges from 0 to 1, and L1 and L2 are the inductances of the two coils. If two coils have inductances of 100 microhenries and 200 microhenries, and the coupling coefficient is 0.5, the mutual inductance can be calculated as M equals 0.5 times the square root of 100 times 200, which equals 0.5 times 141.42, resulting in 70.71 microhenries. When a voltage is applied to a coil, the current does not immediately reach its maximum value. Instead, it increases gradually due to the inductance. The voltage across the coil is given by the formula V sub L equals L times di by dt, where I is the current through the coil. If a 10-volt battery is connected to a 100 microhenry coil, the initial rate of change of current can be calculated as di by dt equals V sub L divided by L, which equals 10 divided by 100 times 10 to the power of -6. Resulting in 10 to the power of 5 amperes per second. When the current through a coil is suddenly interrupted, the energy stored in the magnetic field is released, causing a high voltage spike. This can be dangerous and can damage other components in the circuit. The voltage spike is given by the formula V equals L times di by dt. If the current through a 100 microhenry coil is 1 ampere, and it is suddenly interrupted in 1 microsecond, the voltage spike can be calculated as V equals 100 times 10 to the power of -6 times 1 divided by 1 times 10 to the power of -6, resulting in 100 volts. The energy stored in a coil is given by the formula W equals 1/2 times L times I squared, where I is the current through the coil. If a 100 microhenry coil has a current of 1 ampere flowing through it, the energy stored in the coil can be calculated as W equals 1/2 times 100 times 10 to the power of -6 times 1 squared, which equals 50 times 10 to the power of -6 joules, or 50 microjoules. Both capacitors and coils store energy, but they do so in different ways and have different characteristics. A capacitor stores energy in an electric field, while a coil stores energy in a magnetic field. Capacitors oppose changes in voltage, while coils oppose changes in current. Capacitors are used for filtering and energy storage in DC circuits, while coils are used for inductive coupling and energy storage in AC circuits. Consider a 100 microfarad capacitor and a 100 microhenry coil, both storing the same amount of energy, 50 microjoules. For the capacitor, 50 times 10 to the power of -6 equals 1/2 times 100 times 10 to the power of -6 times V squared, which implies V squared equals 1, resulting in a voltage of 1 volt. For the coil, 50 times 10 to the power of -6 equals 1/2 times 100 times 10 to the power of -6 times I squared, which implies I squared equals 1, resulting in a current of 1 ampere. In summary, while both components can store the same amount of energy, they do so under different conditions and are used in different applications. By understanding these fundamental concepts, first-year electrical engineering students will gain a solid foundation in the behavior and applications of coils and inductance in electrical circuits. Thank you for watching.